In this brief video, we explore a method for adjusting the bed shear stress term, used for calculating surface water momentum, and the Shields parameter for sediment transport in gravel beaches within coastal modeling applications. As a quick high-level refresher, bed shear stress is a measure of the tangential force per unit area exerted by the flow of water on the bed material. We need to calculate the bed shear stress for two purposes. One, to compute the water momentum balance, and second, to compute the Shield parameter. The bed shear stress is then described not only in terms of a drag component, but a drag and an inertia component. And by incorporating the inertia component, the effect of acceleration on sediment transport is taken into account in the bed shear stress term. Now, let's take a quick look at each component of the bed shear stress. Bed shear stress due to drag is expressed by this term, where h is water depth, u is flow velocity, rho is the density. And this guy, Cf, is the dimensionless friction factor, which is described by this term. And if you'd like to get into the weeds a little more, Cf0 is the dimensionless bed friction factor without ventilated boundary layer effects, and phi is non-dimensional ventilation parameter. Cf0 is described by this expression, where g is gravitational acceleration and k is the wave number. And finally, phi, or the non-dimensional ventilation parameter, is expressed by this relationship. And if you wonder what this parameter s is, this is associated with the seepage or ventilation velocity, which accounts for the influence of infiltration or exfiltration on the boundary layer dynamic. Finally, we discuss the inertia term in the bed shear stress. We can compute bed shear due to inertia effects through analogy with the force exerted by water on a sphere in non-stationary flow. In this case, the force on an object due to inertia force can be computed from the local flow acceleration described in this expression, where Cm is the inertia coefficient. Chem is defined as 1 plus Ca, where Ca is added mass. Cv is the volume shape factor, which is equal to 1/6 of a pi for spheres. The inertial force is then the sum of the Froude-Krylov force and the hydrodynamic mass force. And the shear stress on the bed due to inertia is computed by assuming the characteristic grain size to be the median sediment grain size, and the number of grains affected by flow acceleration per unit area. The inertia force is then scaled with the multiplication of Cn and the grain median size squared to give us the bed shear stress due to inertia. In most practical cases, the individual values of Cm, Cv, and Cn cannot be derived from measurement data, so these parameters are replaced by one calibration coefficient for inertia, which is used to describe the added mass of the grains, as well as the shape of the grains and number of grains on the surface of the bed affected by flow acceleration. This inertia equation should be considered with educated judgments, as several assumptions and simplifications were made when deriving it. We explain these simplifications in the caption, along with a link to the literature we used to prepare this material. Hope you enjoyed it and found it useful.